Okay, given Weinstein manifold, you can attach a Weinstein N handle, we say, which is T star Dn. Okay, to this to get a new Weinstein manifold to get. Okay. So attachment happens along. So attach along infinite boundary of M. So do you recall this? Remember, for Liouville manifolds, we have a boundary at infinity, or we could cut Weinstein manifold as a, I mean, we can express it as a Weinstein domain, right? We could cut the cylindrical end, then there's a boundary. So that's called boundary at infinity, okay? So I will give an example, maybe you will recall that. So you attach this to its boundary at infinity. Attach along, not this, sorry. Attach along the boundary of this, the n, which is Sn minus 1, which living inside boundary of m at infinity. And remember, I also mentioned this is a contact manifold. And this is a Legendre. So maybe for that part, maybe I should say with Weinstein comes with Liouville one form. Okay. And the contact form is just restriction of this one form to its boundary at infinity. Okay, so, and the Legendre is just a subspace of this, where this alpha vanishes. Okay, and the dimension is n minus 1. Okay, this is just this story. Maybe on example it will be more clear. So I will give some examples now. Okay, so example. So we know cotangent bundles, right? We know they are Weinstein manifolds. Last time we showed, if for let's say T star n, and where n compact is Weinstein manifold. This is we discussed last time. So let's just actually work with T star S1. So T star S1 is this. Let me color the skeleton different. Oh, okay, here. Maybe red is good. And maybe Liouville vector field also. So this is X Liouville vector field. And red is skeleton. And which is zero section, remember, for cotangent boundary is zero section. Do you remember this picture? So then the contact boundary is this part, this two. Okay, this is the contact boundary of this. I said M. Let's use M for now. Okay, here. Actually, sphere bundle. Because this is like a set of directions, right? You know, sphere bundle or co-sphere bundle, one can say. So this part, and this part. Okay, so now I can, from using this, I can construct new spaces. So how do I do that? So let's look at the description. So I should just choose some Legendres on this, in the infinite boundary, right? In the contact boundary here. But what are the Legendres here? for this dimension, it's just points. So just choose. I should actually choose this circle. I mean, 2 points actually, because n is 1 here. So 2 points. I need to choose 2 points. Let's say I choose this 2 point. I mean, if you know Morse theory, actually, in general, I need to give some neighborhood of this also. I mean, you need to describe the framing, but in Weissen's story, you don't need to do this. It's automatic. So you just choose some Legendrians and complete it to the disk D1. And then complete it to its cotangent bundle. So which is T star D1. So that's the attaching procedure. Does it make sense? And this has a Liouville vector field, of course, because it's also cotangent like this. But this Liouville vector field and this doesn't match, so you need to perturb this one. You kind of perturb it here a little bit like this. But that perturbation makes new skeleton, so kind of you complete this part of the skeleton. Liouville vector field. Just bring it down. Bring this down. So this red part is the new skeleton of the new space. Then you need to perturb this layer also. So what is this space then? What did we get? Is it familiar, anyone? So there's here one hole. There's one hole back and one hole bottom. So 3 holes. Actually, we had this kind of example, three holes, a surface. Sorry? Pair of pens. Yeah, pair of pens. This is the pair of pens. Actually, the skeleton is exactly this thing that I mentioned, right? That same skeleton. If you look from some particular direction, I think. This is a cossphere bundle. Okay. So tangent bundle is the set of directions, right? So set of vectors, this set of directions. So I kind of forget this. I'm divided by positive scaling, basically. So this is a pair of pens. Yeah, I will give one more example. I mean, basically this example, I mean, if you can get these examples, then just I will generalize this to dimension 2, whatever I say here. This is the dimension 1 skeleton, right? This paper happening in dimension 2 skeleton. So, but let's understand what's happening here first. So I can start with this system. Maybe I draw it too tall. Okay. This is skeleton. This time I will attach using 1 point here, 1 point here. I can do this, right? And this is D1. We call it core of the handle, actually. This is core. And T star D1 is just draw a neighborhood. This neighborhood, again, uniquely determined by some stuff for now. Okay. And the new skeleton is, you bring this down like this, along the Liouville vector field. And you kind of perturb Liouville vector fields, etc. And this is the new, this new space after attaching this T star D1 like this. And what is this one? This space? Yeah, one puncture torus, indeed. So it's like a puncture torus. Yes. Etc. So now the thing I want to talk about is what are the moves so on this attaching. The thing is, I can, so this is Legendre, right? But maybe Legendre doesn't make sense too much. I mean, I just give this definition, but at least in this point case, if you move your Legendre along Legendrian isotopy, which means if you move it with isotopy, which is true Legendrians, the resulting space doesn't change. Okay. In this case, you can ignore Legendrian. You can move this point like continuously or whatever smoothly, and the resulting space won't change. Okay. So this is the actual idea. So through the idea, I can change the skeleton, which doesn't, and that won't change the resulting space. So let's do it for this one. Maybe for two.
You follow me. There's a handle attention, but it's not just constructing a space, it's constructing this entire Weinstein structure. With the symplectic form, the little vector field, then you can look at the skeleton, everything is happening here, all of that, not just spaces.
So all the substructures. So as a Weinstein manifold, we can get this. Okay, but I can attach. Okay, maybe I will work on this picture because of time reasons again. So I will erase stuff on this. Where's the tracer? Nerede? Öyle mi? Nerede? Does this happen to anyone? I don't remember. Yeah. Okay. Okay, let's attach different way. Okay, so I won't attach it like this. I will attach like along this point instead. Just I move it a little bit. So as I told you, it shouldn't change the Weinstein manifold. Okay. But it will change the skeleton. So you will see. I get this skeleton. Okay. And I could also attach it here, then I will get the other one. So maybe locally, let's see what's happening. Okay. So just look at very local picture. So I have this skeleton, right? I'm just taking this strip, okay? I attach along here and along here, I get this skeleton, right? Locally. I mean, I could attach here and here, I could get this one. So equivalent means the Weinstein manifolds are equivalent. They are different skeleton, okay? And I could attach to the right, I could also get this one. Okay. Actually, this is the idea of this paper, kind of. This is kind of disk surgery in dimension one, let's say. I can get from this skeleton to this skeleton by moving like this. They seem like same, but so one important. This is not same like them, but one last thing I want to say about this is what about sheaves on them? If you remember microcool sheaves, what happened to sheaves? So maybe I will use some very naive definition of microcool sheaves. Assuming that the skeleton is very stratified, you know, and everything. Microcool sheaves, you can think like on the smooth part, you give vector space, actually chain complex of vector space on smooth part. And a singular part, there is some maps going on. For example, how do we determine those maps? Like Vivek did last time. So for example, Vivek analyzed this kind of singularities, right? He analyzed that if you have this kind of singularity, you need to have I mean, there's convention, so I will use this one. So I will use A, B, and C here. Maybe I should write bigger. Different color. So there's A here. So every smooth part, By the way, this is wrong, okay? Every smooth part you give local constant sheaf actually, but assume, so it's all contractible. So every smooth piece of the skeleton, you give some vector space. Yeah, let's say like that for now. Vector space A, B, and C. Chain complex of vector space actually. And this shape tells you the maps between them, kind of. So here you have this kind of map. Here you have this kind of map. This is my last talk. I'm a PVX talk. Okay. So you can just take it as a definition. But and actually there is also something here. It's called micro-locus talk.
Could say a little bit more what you're doing. So now we have this space, and we're trying to understand its wrapped Fukai category.
Yeah.
You know, it's equivalent to some kind of sheet.
Yeah. So I forgot to say which category I'm working on, right? So micro-locus sheaves on this skeleton I'm working on, okay? And it's equivalent to wrapped square category of resulting Weissman manifold. Okay. This is, I think, Vivek measure. Weissman sector in this case, yeah, because there's a boundary. Boundary also there, actually. So I'm just giving you on this category an object, okay? Which means an object is actually kind of collection of sheaves on this part where there is some maps around singularity coming from micro-locus sheaf geometry, which you need to work out. So this is not part of this talk. But there's also this X and Y part. Anyway, never mind those parts, but I mean, there's also
I think you don't
stocks.
have to rush so much. You don't have to, just let's work this out. I think without understanding this dimension, you won't be able to understand anything about four dimensions.
You want to do shift theoretical understanding of this, or?
Just, we can say in the end, the four-dimensional case is similar, and then if people are interested, they can read the paper.
Okay.
So let's make sure that people can see what's going on here, because I think people are lost.
Okay, so yeah, if you are lost here, so maybe we should stay here.
Yes.
Okay, so let's do this stuff.
Start from the beginning, from the picture, what we're doing from the picture. We have this skeleton, and from this skeleton, we're trying to determine this wrapped category of the whole thing, of this complicated manifold, punctured form. Okay, not so complicated, but kind of complicated. We're trying to do that by piecing it together from we have smaller pieces, and we want to understand the small pieces, and then we want to kind of glue them together to get the big thing. So now we're analyzing the small things.
So actually I won't get the big thing, but just trying to say that even the small thing is different. Okay, so the sheaves change from this skeleton to the other skeleton where you move this 2 point like that. Okay. Okay, so still, maybe I won't explain.
But the category doesn't change, right?
Yeah, the category doesn't change. So idea is this is a one object on this category, right? This object in this category will go to some other object in the same category. So it will go to different thing. So how I know that? So because first of all, this will give you a different representation of that same category. So this is the same as micro-locus sheaves on this thing. Okay, so let's see so you can think this transformation like this. For example, when I move this part, so this is my sheaf, right? When I move this part like this, so assume I have some stalks here, A, B, C, X, and Y, right? This is my sheaf. A micro-locus sheaf whose stalks are A, B, C, X, and Y. So when I move this, what about the stalk here? What will happen to that? I mean, it's not affected by anything, right? This part, this moves, and this stalk is still A. So this is A. This is C. This is X. This is Y. Those are not affected by this. I won't discuss this category, by the way. So let's just go to the next picture. So you pass this picture. This will be still X. This will be still C. This will be still A. But what about the middle part? First of all, let's put a question mark here, but what about the arrows? What is the direction of arrows here in this side? If it's up, it's left direction, right? So here is down, so it's right direction. It's opposite. He's down, it's right direction, up, left direction. So first of all, arrows even flipped. Can I still put B here? I'm sorry? So this DG category. DG drive, do people call DG drive those categories? But don't think about, so those maps are not morphisms. Everything is a one object right now. Everything is a one. So think like this shifts. What is shift normally? Shift is sections and restriction maps, right? Yeah. Yeah. So this category, this category is representation of this quiver. Okay. Forget about X and Y. You have A, B, C, right? So it's a representation of this thing, this quiver.
Yes. So
you mean ABC here?
Yeah, this question so, also
maybe let's think shift easier even, think like.
What's the mathematical definition at this point?
No.
I think people can understand.
Yeah. Actually, it's very simple understanding of the shift, right? What is shift? Stokes, right? Stokes and restriction maps, right? So think, I want to give a shift on this thing, right?
Not that thing on the line.
But
so it's almost like a sheet on this horizontal part of this, but it's a micro sheet. So it's a little bit different than a sheet on this, like in Vivek's fall. It can jump along this vertical pieces.
Okay. Yeah, okay. You can also give a shift on this whole thing, but since Vivek didn't say this, so I won't say this also. You give shift here, and stokes are A, B, and C. And these arrows are restriction maps. Why there's no restriction map here? Because it's locally constant there. It's just trivial there. So I don't have an arrow in this region.
Isn't the local constant?
And local constant shift has just one stalk and monodromy. So if this is contractible, there's no monodromy. So it's just constant shift. So in this part, it's just contractible. So it's just constant shift. In this part, it's constant shift. In this part, constant shift. Yeah, but here it's not constant shift. Therefore, there's a restriction, non-trivial restriction map. But why this is only one arrow? And this is Vivek's talk. So you can discuss in discussion session if you like. Why at that point is one arrow?
Shift A.
Sorry?
What is the support of shift A?
It's A again. So I support, you mean, okay, this whole thing. Everything, it's not, never zero. Support is the part where it's not zero, right? It's usual support. So it's everything. Okay? So make sense? Sorry?
They change the errors, so they only derive the errors, right?
You mean this and this? These are DJ equivalent or derived equivalent also. I mean, whenever some two things are DJ equivalent, it's in particular derived equivalent. Okay?
So he's just saying if you think of them as vector spaces, actual representation categories, they're not equal.
Yeah. So you should. You need to take a chain complex of vector spaces, and these are chain maps. Actually, so that's what's going on.
You need to take DG representations, and the category of DG representations of those quivers are derived.
Yeah. So
this is a correct statement.
Yeah, I don't know.
Yeah. I mean,
but it should be obvious from this picture because they're both modeling this category wrapped entire category, and that category is it only depends on the manifold that this gives the not the skeleton. So that's supposed to tell you that these representation categories are derived equivalent.
It is known from representation theory also, right? There's a sync moves. You replace sync with the source, etc. You know those moves? So I mean, from representation theory, we also know this is true. But anyway, from this also we can reprove that fact. So which means this representation theory and this representation theory, this representation category are the same. Okay. But this question mark, okay. So what is the stalk here now? Maybe I ask this. The thing is, I don't actually know answer immediately, but it's not B naturally, because now there's an arrow from A to something. So this is arrow from B to A, right? Arrow from B to A. This from A, so I don't know if there's there's no natural way of defining an arrow from A to B from this data. So this should be something else. This should be D. Okay. It can be determined somehow, but it's different. So just I'm trying to say this. Okay. So as you see, we get something different. And this part is different.
Which forms like X and Y differ from A and C?
Right.
Can I think about and X and Y as like also shifts?
Yeah, if you remember, there was a micro stalk, right?
Yeah.
So this arrow uniquely determines a stalk here, but this arrow, this data determines it. We can discuss in the discussion section if you like, but there's a way to. That's how you will kind of figure out D, because you know the micro stalk should be X, and you should put something here such that so that the micro stalk is X here.
Mean also that the picture not equivalent by X and Y. So I don't know.
Okay, so those are different moves. Okay, so I mean you are bending it, but those are different moves. So, but in short, let's look at this. If you look like this line and this line has a different shift on them, right? So they are different actually. This line and this line. Okay, they are different shifts on them, right? Okay, so yeah, sorry. This is X and this is Y. Okay, so probably
Those representation categories are not the same if you think of them over vector space representation. Isn't this like some theorem about we can change if you have an agent thing, you can change the arrow direction and the result the category with the same. So it's right. Just derived, it's only derived.
I mean,
Well, this only the derived.
the reflection is the path and the source. The path of the reflection and the source of the energy point is not just like there is an equivalence in the reflected panels in the point if all panels are coming to this point or they're all going. So it's yeah, so but one is the projected spread and the other is the injected spread.
Yeah, but I don't know this very well. That's why I'm asking, because you guys could connect to what's going on from that perspective. That's why I'm pushing this. Okay, but you at least agree that there is a DG equal, like derived equivalence if you look at DG representations of these two categories. This we agree.
I mean,
So that's this statement. It's already kind of non-trivial, right? It's not already kind of, it's not.
I mean, there is a theorem in the representation theory where if you have two trees and if you choose any resource in that tree and just make the other arrows go out of from source, their representations are DG equivalent. So this one instance of this. So there's a tree. I choose this as a source here. You can choose source or sink. So you can just choose sink, and they're DG equivalent. But kind of this is a geometric proof of that fact. Okay. So let's do the surface case. Okay.
The claim is that attachment, after attachment, the perturbation is unique up to blah blah, and right.
So I mean, after you attach this,
I mean, one can handle attachment is unique up to.
I mean, it's unique up to determining this Legendrians. So once we determine those Legendrians here. And it's up to their Legendrian perturbation. It's unique. So.
And the perturbation data determines really this picture.
Yeah, perturbation data actually determines the map.
And ABC and all the.
Yeah. So this perturbation gives you some equivalence in the category level because it doesn't change the actual Weisser manifold, so it doesn't change the category. So it actually gives the map. Actually, this described in the Guillermo Kashiwara-Shapira paper, how this determined, how this move determines the actual shift, how actual category moves. So they actually study this. So anyway, any other question? So we can do this in the also in higher dimension, right? So let's say take T star surface. Let's call the surface M now again, or let's call it M, and M is surface. And compact surface, okay? Then you can attach handles to this and to get the new manifold. So the dimension of this is a 4-dimension, right? Because surface is 2-dimension, this 4. So you can attach T star D2 to this one. Maybe I just give you an example. Since I don't have much time, so let's just focus on examples, right? Easy to understand. So let's say M is surface, torus. So this T star torus, okay? And this is the skeleton part. So it's T star, this is the dimension manifold. Then you will say this, okay, how can I attach this to this? Boundary of D2, so it's S1. So I need to give S1 on where? In the contact, in the infinite boundary of this T star torus, which is the sphere bundle of the torus. Sphere bundle. And what is the co-sphere bundle? Again, points on this with directions, right? So I cannot draw this co-sphere bundle right now. But instead, I can specify this circle. So this should be Lagrangian, actually. Lagrangian. I can specify this Lagrangian on this co-sphere bundle, just looking at the torus, this M. So there's T star M, right? Up. And there's S star M, actually. So again, what are the points of the co-sphere bundle? Points on M with direction. So for example, I can just draw a circle. This is a curve on M. But if I give a direction at each point, what is this? If I give direction at each point, it is actually not a subset of co-sphere bundle. And there's one more thing, which is to be Lagrangian, this direction should be perpendicular to your curve. That's Lagrangian condition, okay? So I cannot choose any direction. I need to choose a direction which is perpendicular to the curve. So there is actually two choices. Either I will choose this direction at this point or this direction. So therefore, so this S1 can be described like this. The attaching circle can be described by a circle, simple closed circle, curve, you can say, and a direction, perpendicular direction. Let's say this direction. So I will just draw hairs, okay? So now maybe let's stop. Does it make sense what it means? So this is actually a subset of co-sphere bundle, because at each point I'm giving you a point on M and a direction. So it is actually a subset of co-sphere bundle for this reason. And it's S1, and Lagrangian condition is just this direction should be perpendicular to your curve, which is satisfied. So this actually, I'm just giving you as exactly this one. Then you attach T star D2 to this thing on the co-sphere bundle, okay? Of course, I won't be able to draw actual picture because it's higher dimension, right? But this is just the way I can draw it here.
Maybe you can give like the exact thing here, like What is this picture in this dimension?
Yeah. So for example, this circle here, I mean, this M here is actually corresponding to here. M is here. And I could actually give this data how? I could give this data without actually drawing this part, right? I could give you a point and a direction. Here, I could also do the same thing here. I could say, okay, this is point and this direction, and this point and this direction. If I do this, what this means? This direction means up. So it means actually I am looking at this point, but in this cosine bundle, in that direction, which is this point actually. I'm meaning by this point and this arrow, I mean this point. By point and left, I mean the point at the bottom. Okay. So this actually corresponds to this data, which tells you which point you should attach your handle. Okay. So basically, then you attach a disk to this thing on the cosine bundle, and you then kind of complete it to the T star D2 and get a Weinstein manifold. Does it make sense? Okay, so let's attach one more thing. I mean, I can attach not just one, I can attach multiple, right? I can attach this one more like this. Okay, so how much time I have? 17 minutes. Maybe this is simple. Maybe I will just work with two curves. And I will say what happens with this. So now let me tell the goal of this paper. Okay. So the paper says this determines the Weinstein manifold. Do we agree with this at least? So because Weinstein manifold, T star torus, and I give you some handles. So it gives a new Weinstein manifold, right? So this paper gives some combinatorial or like a moves on these curves. Okay. So it will give some moves and it will change the collection of this curve to new collection of curves. The claim of this paper is, so let me tell you actually this move. So this paper says this. So let's say this is the curve 1, C1. This is curve 2. Okay. And let me actually follow my picture because otherwise I will mess up. Okay, maybe let's from now on focus on the analyst so that I can draw everything easier. So the thing that this paper does is this. So it will define a mutation on this curve, so such that it will change this collection of curves into a new collection of curves. Okay, so I will first show you how this mutation works. And since this mutation works, so let's say if I do mutation at C2, it just do change this collection in the neighborhood of C2. So I can just focus on neighborhood of C2. And neighborhood of C2 is just analysis. So from now on, let's work with analysis. There's this analysis, and there's this C2. Okay. Actually, let me say this is C3. Let's say this is C1 and one more color. C2. Okay, I kind of cut a piece of this. So I just cut the neighborhood of this blue curve. So let's say there's one more curve here. So let's say this is C3 and this is C2. Okay. I just look at the neighborhood of C3. So it's neighborhood of C3. I have this picture. So there's a mutation operation on this. So mutation at C3. Okay. So this mutation does the following. So first of all, for C3, it just changed the orientation. We call this Pintar orientation, okay? So instead of this way, C3 becomes that way. Okay, it does this to C3. So C3 prime now, this new curve. C1, so if the intersection is this way, so you can just look at the intersection number here, the positivity or negativity by right-hand rule. So this fin is going up, blue fin is like this. So with right-hand rule, this is positive. So it's positive intersection, we say. Positive intersection. So this negative intersection, this opposite, if you look at it, this is like negative intersection. So at negative intersection, it doesn't do anything. So this curve just stays as the same. So C2 prime is just C2 actually. At positive intersection, here, it does it dan twist on this curve. It does dan twist. Like this way. And the orientation is the same. Okay.
Right. Yeah.
Yeah.
So we draw now. So in the last minutes, the space T star M, right?
So no, T star, actually this is T star M is this white part, okay? T star torus actually. Whole space is T star M, union, T star D2, corresponding to C1, you know? So let's say times 3, let's say. So I attach T star torus, 3 T star D2, sorry. So I mean, I start with T star M, so at coordinate bundle of torus. Then I attach 3 disks to that, so I get a new space. So it's no longer coordinate bundle; it's something else. Like in this example, right? It was T. Sorry?
Do we have as Lagrangian subspace our initial?
Great remark. Yes, indeed. Okay. So that's actually part of the paper. So we want to understand that Lagrangian. Sorry?
We choose now another one's Lagrangians, which is C1, C2, and C3.
So we attach new Lagrangian disk to that. Okay, and it becomes a singular Lagrangian. If
okay, it's still like a Lagrangian.
There is a unique choice for the framings to make it Lagrangian, right?
Yeah, so true, but that's not actual thing. So this is the resulting thing is a skeleton, right? And skeleton itself has Lagrangian for Weinstein case, exact Lagrangian. But this part, this torus is still sitting inside your Weinstein manifold as a exact Lagrangian itself. Okay, so it's still inside your Weinstein manifold. Yeah.
So you mutated this, for example, C3, you said, right?
Oh yeah.
But in the left-hand lower background, you also did some kind of mutation, but the mutation was kind of relative to 2 of these things, right? But I mean, at least on the quiver level. So
yeah. So this mutation actually. So let me find the analogy between this. Actually, this analogy is this. Analogy is converting this blue fins this way to this way. This is the analogy here, not the intersection part. So I mean, for what happens to C3? Directions reverse, right? So that kind of mutation happening here. Maybe two of them, let's say, both of them. Both of them. The pair of, I mean, pair of them is better word, yeah, pair of them. Because pair is the here, yeah, exactly. So I mean, pair is the, so here S1, here are circles are object, there is a 2 points are object, right? The pair actually I mutate there, so the arrows rotate. So that exactly corresponds to C3 here. So I mutate C3, the direction reverse. Actually, that's the I want to focus from after this picture, if I have time, and just do analogy between dot picture and in this C3 picture, okay? But let's maybe at least combinatorically. I mean, you see, right? A priori, this is a completely different picture, right? Not super completely, but I mean, it's different picture. So it would give a different Weissman manifold, you would say. So this is a new Weissman manifold with different new Weissman skeleton. But the result of this paper is this. It says this two Weissman manifold is actually the same. It doesn't change the Weissman manifold. So this just generates a new skeleton.
So without C1 and C2, just reversing the pairs of C3, you would get the same Weinstein manifold, right?
I mean, yeah, with C1 also, I mean, all included.
Without C1.
Without C1 also is still true. Actually, that's the actual part. Sorry?
This is the right manifold.
Oh, yeah. So C3 case is this. And actual mathematics is actually happening here. C1 and C2 is not that important, actually. It just follows from, I mean, if I can draw the picture for C3, it's not that hard to prove this result. Also, I mean, if you do this, it doesn't change. Actual part of the proof is just reversing this C3 doesn't change the manifold. But let me, since I give you some remarks on this, if you
once you make the statement, so you need to change the C1, right, to get the same manifold. You can't just reverse the arrow of C3. You need to.
No. Of course, I'm just saying this. If you just work with C3 and nothing else in this picture.
Okay, if there's nothing
else,
other curves that you use.
You still change, then it's true, right? But if you attach this, you need to change the C1. But that change is kind of forced by this move. I mean, this move forces your C1, it kind of automatically does this move to your thing. I mean, basically just proof boils on this.
Knowledge here would be so you have the 2 points, which is S0 and S1, and you change the orientation. So instead of taking the inward pointing ones, you take the outward pointing ones. Co-orientation. Outward pointing arrows. And that kind of, you can also realize that change as moving one on top of the other.
Yeah.
And that's what you did here.
Yeah, and here also same, just higher dimensional version. Actually, nothing different here, and not nothing different, but it's just higher dimensional version of it.
Sorry, may I ask a question?
Like just on torus, just take appropriate, I don't know, do we have some Lagrange form? Just, I don't know, without these 2 additional dimensions. Because we have 2 cycles and cycle A, cycle B, and
you mean cycles are this? You mean?
Yeah.
Okay, which space are you taking? What is your?
Just M.
Yeah, any M you say.
M. Just like a torus without T star.
Okay, but that is what we Weissman manifold. I mean that will be different story. I mean, you can make it Weissman manifold.
Two-dimensional example. Why do you want to take a torus? This is the 2-dimensional example. Then in one higher, so this is S1. That's S1 cross S1. So here you take an S0 inside S1. There you take an S1 inside S1 cross S1. Something like that. I mean, so
just without,
So is there an isotopy that takes this picture to that picture?
Yes, exactly. So, but there's some tricks. But that's the idea. There's a Legendre isotopy you can do, and you end up with this kind of curves. So therefore, it doesn't change the Weissman manifold, but it changes the skeleton. But why changing skeleton is important? I mean, it's important, of course. I want to generate lots of skeleton. One other thing is this. This skeleton has this torus as a subspace, right? So there's this torus in this skeleton. I mean, this torus. So when I mutate, I create the same Weissman manifold using a torus again, using these curves. So I mean, let me say again. Okay. So I have this torus and this curves, right? Now I mutated. I get a new torus and new curves. I won't draw all of them, but at least draw this one, like this, etc. Okay. So now I claim this, right? So this both create same Weinstein manifold when you do attachment, but different skeleton. But the thing is, this torus doesn't correspond to this torus anymore. How do you understand this? Maybe this shift understanding may help. Okay. I mean, there's a way to distinguish these two torus by looking local systems on them. You can distinguish them in the category level. So they don't correspond to the same object in the category anymore, in the Fukaya category. So when you do computations. So that's a computation part. You do micro shift.
Statement. I think you just have to say the statement clearly because I don't think people understood the statement.
Statement is this. This torus here and this torus there now living in the same Weinstein manifold, right? Because they give the same Weinstein. So between Weinstein manifold, and and there's S living in this Weinstein manifold, the surface, your torus, and the other torus living in the same Weinstein manifold. These two Weinstein manifolds are isotopic, actually you can show, but not Hamiltonian isotopic. So symplectically they are not the same. So you get a different actually torus. So what does it say?
So what do you mean by different torus? You mean that the image of the torus under this map is not a torus?
No, this is not the image of that torus. This is a new torus. This is not image of this torus. So I'm not saying this torus is exactly this torus. It's not happening like this. So this Weinstein manifold doesn't construct same. I mean, there's some moves involved there because you are not using actually same torus. If you, it's not that maybe it's so easy thinking.
Except that we take that these two Weinstein, the fact that these two Weinstein domains are symplectomorphic, let's just take that for granted. Okay, let's say that's a difficult theorem. Okay, let's take it as a black box. And then with that, then you can understand because it's impossible. I mean, you feel like people will just look and understand. It's impossible.
Okay.
It's impossible to understand why that's true. So let's just assume that for some reason, someone told you that those two pictures define to you the same Weinstein manifold. There is an isomorphism between the two. But the point is that isomorphism doesn't take the first torus that you started with to the second torus that you ended up with. They're different. Now you can think of these two tori living in the same space, and they're different. They're not Hamiltonian isotopic to each other. It's kind of like, again, finding different toric models. Finding different C star squares inside your Loenga interior or cluster, right?
Yeah, so that's the actually, I mean, there are two things comes out from this. One is this mutation operation gives you new torus, right? I mean, since we're working with torus here, it gives you different toruses each time you mutate. So you can mutate this again, right? You can mutate this again, you get a new different torus. Actually, all of them will be different, assuming something. So you can actually generate infinite many tori in some cases, okay, via this mutation. So you just, assuming your mutation doesn't repeat, you don't come back to the same curve collection, you always produce new tori this way. And if you know about cluster theory, local system on this tori actually gives you algebraic torus, okay? Maybe. So you actually giving a chart on the Fukaya category or microcurve category. So, because I mean, you are giving
in the mirror, right? In the mirror.
It's not in the mirror only.
Right? But of course, the presentation is again like depends on your seeds and kind of your starting data. But the object is a global thing. So let's say a very simple example of the relation between the associated cluster variety and the Weinstein manifold.
So it's like this. Let's take microcurve category of Fukaya category, okay? Fukaya category of your Weinstein manifold or microcurve on the skeleton. Okay. So first of all, those tori are part of the skeleton, right? Or you can think like this. Okay, this torus is part of skeleton, right? Would you agree with this?
why did you write micro sheets on torus?
Torus, yeah.
No, and that's it, right? And that's it.
So this is local system. It's difficult to explain on the microconscious side. And maybe it's better I do this because
You took micro local sheets on skeleton, and then you write local systems on torus, embed into that, something like that, right?
oops, yeah, sorry, I did it wrong. This, which is spelled. So this skeleton which is torus union disk, and torus embeds into this, right? Therefore, microlocal shifts on the torus embeds into microlocal shifts on torus union disk. But what is microlocal shift on torus? There's a fact which, if you have smooth thing, micro shift on that thing is just local systems on that. Therefore, just local system on torus embeds inside this. But there's the other torus, right? The mutated torus. Local system on mutated torus prime, let's say, also embeds to this thing. If you compute local system on torus, actually it's representation of pi1 of the torus. So it's actually algebraic torus. Let's see. Anyway, so T, and this T prime. So the algebraic torus embeds into microsheaf category. So kind of I'm giving a chart of torus in my microsheaf category. But furthermore, I know how these two surfaces related, their local system related. How I know? Because I don't know actually right now because we didn't do computation. Right? From this thing, you can actually compute how this and this related. There's a map between them. I mean, this tori, I mean, how to say, they have some intersection and there's a kind of transformation. I mean, there's a map from this to this when they intersect. And that map is actually, this paper shows, is cluster transformation. So it's like this. You start with that surface in this Weinstein manifold. It gives you an algebraic torus chart on the microconscious category. So you mutate it, you get a new chart, algebraic torus chart on this microconscious category. And this first chart and second chart related by cluster transformation.
That's the variety of the Weinstein manifold. There are different objects which are related by this story.
Yeah, so it's not like a cluster structure of Weinstein manifold. It's cluster structure of Weinstein Foucault category of Weinstein manifold. So it's not like Weinstein manifold has a cluster structure here.
Oh.
Yeah.
It actually does. But so then you can also start with the cluster, but just the leaves of the cluster variety, the X cluster variety. You can consider this imaginary part of omega symplectic structure, and for some certain choice of omega, if you choose the right leaf in that deformation class, then that symplectic manifold is actually this kind of symplectic manifold.
Okay, but then you ask to this, you get another cluster structure which could be different after, right?
A priori, yes, but
It's not.
It's so here you're only using the symplectic structure, some kind of shadow of this whole symplectic structure on your cluster array. On the other side, you're actually seeing it as a cluster array, like with its complex structure.
I think this example is also simple from the Foucault category point of view. So we just replace C1 prime with just a cone of morphism between C1 and C2. And we have zero morphisms from C2 to C couple to C2. That's why it doesn't change C2 nowhere. Replace C1 by the cone of morphism from C1 to C2. It is the point of view from the Foucault category, I think.
Yeah, I mean,
it is just it happens.
Let's say it's a good conjecture.
Yeah, I mean, I'd like to think about this because I didn't understand right now.
If C2 was was a spherical object, like just the cycle that's there, But this it is not.
No, you have to be careful. You have to be careful.
I mean, maybe I can tell you what, I mean, I'm over time. Last thing, which is analogy like this. So what you do here in the skeleton, there's a disc, right? D1 here, actually here. There's the D1. You kind of contract it and recreate it, right? That's the move. That's actually called disc surgery. This move. You contract this disc and recreate it. Disc surgery. So actually, you do the same thing here. So, I mean, actually, C3 is not good here. Maybe let me erase C3 and just do it with C1. And let's save this mutation at 1. And then I finish. Not this color, but anyway. Okay, let's say we have just one curve. The C1 is just this way. And the mutation, if you mutate at C1, it's this way, right? Just change the orientation. And the move is this. So this C1, you attach a disk on this, right? So let's say that disk is here. Maybe this is not a good explanation. Now I kind of already regret explaining this. Anyway, so there's a disk attached to the C1. So actually there's a disk somewhere here. So you contract that disk to a point along the way. Then you recreate that disk. Which recreating that disk is kind of, you change like that. So this is a new disk actually. So this attached disk is now new disk. Which is this is the analogy between this and that. So that's actually proof. So maybe geometrically. This is called disk surgery. Anyway, so maybe I should finish. Sorry.
You said there is a Legendre identity between the two, let's say, C bonds.
Yes.
It's part of it, but now you say that you pinch this.
So that pinching can be seen as a Legendre isotopy. So very quickly, let me show you this picture. I mean, at some point, I cannot show the whole picture, but maybe from my note you can see. But at some point, you come to this picture where there's this plane, and there is this thing, which has this circle up, and then this is the cosphere bundle here. So using the contact form, contact form makes this goes this way. I mean, that's the, Legendre isotopy, sorry. That's the Legendre isotopy. It makes this circle smaller. So it makes it smaller. So it makes it like this. So if I watch the movie, this up gets smaller. So therefore this also gets smaller. So it makes it even smaller. At some point it becomes a point. Point with all the directions actually. And it becomes a point. Then it re-expands. So it's like the points are actually, there's a circle, all points are coming to the origin. Then they pass the origin, right? So they are going to the other direction. So now they re-expand. Therefore, now they are looking to this direction. So they are going to that direction now. It's growing like this. Actually, it's exactly same as this picture. So not exactly me, but this surgery can be realized by Legendre isotopy. I do Legendre isotopy on the skeleton. It does this surgery thing.
In this picture, during the isotopy, X and Y they found the same vertical fiber.
At some point.
This is the.
That's also happening there, but it's like this. At here, it has all the directions, right? What is the thing? What is the thing which has all the directions? It's just fiber, cotangent fiber, if you think. So actually, pictorially, at that point, it becomes this. Plumbing sector, we call it. I mean, that's the intermediate step for dimension 2. For dimension 1, this was cross. Dimension 2, what is cross? Zero section and fiber at origin, right? In dimension 2, same picture. Zero section and fiber at the zero, which is this. So same picture happening. But this circle is not like this. It stays like on the origin. It's not like staying like this on the cosine. It stays like this. Just auto origin. So then it resolves again. So I mean then it becomes this again. So if the picture is this, this one comes to this, then that. Sorry.
And this legend in isotopy does not extend to a Hamiltonian isotopy.
No, it extends.
But you said that these Weinstein manifolds are isomorphic, but not through Hamiltonian isotopy.
But the thing is, that surface is not that surface. So that's the thing. So it's a little bit strange part. I agree. Right? Because I'm not drawing. This picture is not that picture, as you see. This is actually not that picture. That was annulus. There is no annulus here. So because I did something to annulus first to create this new picture. So I kind of first carried that picture to this picture, then do degenerate isotope on this picture. But this is not the original picture. So there are some steps which is not apparent here. But you can see me in my lecture notes, or you can ask me if you want to see big full picture. But that's the actual invariance. That's the actual thing that happening here. And this move here change structures. That singularity happening here. Yeah.
Okay. Other questions? Online questions? Okay, let's thank one.
Thanks.